Hello everyone, welcome to this video. Thank you to everyone that has subscribed, and for the times when you can be bothered to make a comment, I appreciate it. And if you haven't subscribed yet, go ahead and subscribe and join this fun study group. A lot of your work in the laboratory will involve you using reagents to accomplish a task. And the reagents will often come in concentrations or at a state that you cannot use as is. So for instance, if you want to go analyze some cells or like some tissues or prepare reagents that will break open cells or tissues so that you can extract the components in order to study it, you may need to make what is called a lysis buffer. And this will have components that will indeed break open a cell. And the breaking open of the cell can be in a gentle way so that you break open only specific components of the cell, or in a harsh way that breaks everything open because you're going to extract everything. And so in these scenarios, you often need to make the reagent that you need to use maybe communicated to you in terms of molar concentrations. So they may say make 1 molar solution, make 1 molar of tris or 50 millimolar of tris, or they may say make 8 molar of urea or millimolar concentrations of urea. So let's go over that. We're going to talk about measuring the number of moles or measuring the molar concentration that is required for your experiment without using formulas. I found formulas entirely useless going through my education, because it's kind of like me saying, hey, let me explain to you how to do this in Swahili, for instance. Like I find formulas are trying to teach a concept I don't understand or I'm not familiar with, using something, i.e. formula, that I'm also not familiar with. So I prefer to talk through things, and then if you prefer to use formulas as a shortcut, that's fine. A molar concentration, when you're going to measure molarity, the molarity uses the unit of moles. So just as we measure distance in meters, time in seconds and minutes, the number of a substance that we want to use in our solution uses the unit mole. So you can think of it also as how we say a dozen instead of 12. So if you go to the shop, you get a dozen eggs, it means you got 12 eggs. So the mole is just this unit that communicates a certain number of particles. And the certain number of particles, when we're talking about chemicals or compounds that we're using in the lab, turns out to be 6 by 10 to the 23rd particles. And so that's what a mole is. And for our purposes, the mole equates to the molecular weight of the compound, of the chemical, of the reagent that we are measuring. So whenever we're talking about a mole, we're referring to the molecular weight. The molecular weight is in grams. And so a mole is actually referring to grams in a certain volume. And the volume is 1,000 milliliters or a liter. And so what you really are doing in the lab is just adjusting. If you're not making 1 molar, and you don't need a liter, then you're just always adjusting. So you're just scaling all the time. So if I don't want 1,000 milliliters or 1 liter, I really just want 100 milliliters, then I'm scaling that. And so instead of it being the molecular weight, I'll have to adjust a tenth of it, because I'm not doing 1,000 milliliters, I'm just doing 100 milliliters. Then it's a tenth of the molecular weight. The thing to keep in mind is that while a mole always refers to 6.02 by 10 to the 23 particles or molecules or atoms, the weight is actually going to be different for different chemicals or different reagents. Kind of like if I counted 12 black-eyed beans, the weight of it would be different from the count for 12 oranges, because they are different sizes, different items, because they are different. In the same way, the weight for tris, for instance, is the molecular weight for tris, for instance, is different from the molecular weight for salt, sodium chloride, and it's different from the molecular weight for glycerol, for example. And so when we say a mole, we'll always refer to 602 by 10 to the 23 particles. However, the weight will be different. Avogadro's number is 6.022 times 10 to the power of 23. And this is when you're writing it in scientific notation. So obviously when you're actually writing it as a number, it will be 6022 with zeros exactly after it. And so this is apparently pronounced 602 sectillion. And that's according to a TED Ed video, which I have linked in the comments. You can have a look at it. It's very entertaining. So this 602 sectillion particle is a quantity that is known as a mole. And the mole is used, therefore, to represent a quantity. So the mole happens to be so large because it is used to reference items that are so small that you can't even see it. So we're talking molecules, atoms, that are so small that you can't see it, chemical entities that you'll be weighing out in the lab. And so when I tell you to go make 1 molar of any reagent or compound, the first thing you're going to need to find out is how much does it weigh. And so once you know how much it weighs, then 1 molar of it is actually the molecular weight or formula weight of that compound. And specifically, it's in a volume of 1 liter. Since if I told you to go make 1 molar of tris, the molecular weight of tris is 121.14 grams, and it even says per mole. And so you go ahead and weigh out 121.14 grams, and you would dissolve it in a liter because that amount is always referenced or pegged to the volume of 1 liter. So if you're going to make less than a liter, then you would scale how much of the tris you would weigh out. If you also don't want to make 1 molar actually, but you want to make half a mole, or you want to make a quarter of a mole, or you want to make 0.1 of a mole, then you would also have to scale it. And so that's all we're doing in the labs with all these calculations. We're having to scale everything in reference to the given 1 molar quantity of the chemical, of the compound, of the molecule, which we know is referencing 602 sectillion particles. So if I want half a mole of tris, what would it be? Would it be half of 121, the molecular weight, or what would it be? Yes, it would be half the weight because we want half a mole. So instead of 121 grams, we would weigh out half of that. Now, what if I want half a mole, but not in a liter? I want it in 100 milliliters, so 10-fold less, 10 times less. Then it would be, first of all, half the molecular weight because we only want half a mole, and then 1/10 of whatever that half molecular weight is because we only want 1/10 of the volume. Now that we have the practical side of how to calculate a mole knotted down, I will add that the 602 sectillion molecules that a mole refers to actually comes from the weight of 12 grams of carbon-12. So that's the reference. That's the standard that everything is referenced to. So this 602 sectillion molecules, atoms, does have a scientific or actual quantity basis, and that's that carbon-12 was selected as the referencing standard, and 12 grams of it exactly is what is used as the referencing standard. All right, enough math, enough numbers for the day. I will leave you here. Now, the solution that you need to make may also be communicated to you in terms of percent solution, particularly where you've got liquid reagents such as Twin or other detergents. I have a video on here that talks about how to make percent solutions, so go ahead and take a look. If you haven't subscribed, go ahead and join this fun study group. All the best with your experiment. God bless ya. Bye.